All right, here we go. Welcome on in, everybody. Looks like we're set. I think everything is set right. Welcome on in. You'll have to forgive me. I am not feeling well today. I have definitely gotten a cold or some kind of a thing, and I do not feel well. I've not slept in a few nights very well, and I have this strong sinus headache. So if I seem a little out of it today, I'm not feeling very good. So just forgive me if I have to pause and sort of figure out what I'm talking about for here and there. I'm not 100% today. So anyways, we'll move ahead with our discussion on systems of equations. And so that way you can keep working on stuff, right? You can keep moving ahead. Systems of equations is one of those things where it's pretty much taught the same. So if you need to find a video on YouTube to watch, do that, right? There's videos posted in Canvas. There's videos available in the Delta Math. There's one I'm going to show you today. And the good news is it's all about the same, right? It all sort of amounts to the same stuff. And also the good news is once you know how to solve these systems of equations algebraically, it's pretty much the same thing every single time. There's a couple of those details you have to look out for. Like remember before when we had the no solution type situation, or we had the dependent system where the lines were on top of each other. You have to be a little bit careful about that. But that's, maybe only a few % of the time are you going to get answers like that. And all you have to do is know how to recognize the answers. It's actually not too bad once you sort of don't memorize how to do it. Just if you think your way through it, like last time I was talking a lot about conceptually understanding the systems of equations. If you can conceptually understand what's going on, and then you bring back those pictures, which I'm going to do a quick review from last time, but you bring back those pictures of the situation where you've got the two lines that cross at a point, you've got the two parallel lines, and then you've got the two lines right on top of each other. If you can kind of visualize those when you're doing the problems and think your way through what the answer should look like, you'll be fine. So it's one of those things that takes a little bit of work to get the algebra to come out right. But once it clicks for you, students are pretty much good to go, and they can reliably get them on exams and stuff like that. Plus the fact that it can take a lot of work to solve a system of equations, but the good news is it only takes very little work to check your systems of equations. Once you have a solution that you think is a solution, checking your work just takes a few seconds, right? Maybe up to like 10 seconds if it's a complicated problem, but definitely worth checking that before you put it in Delta Math and maybe use up one of your tries or something like that, or have to do a whole new problem. So, and students generally do well in systems of equations. Like I say, the ones that sit down and say, okay, I need to learn this, and they do the homework, they're good with it. It's also helpful. People that are taking Math 3 have lots of different routes that they're going. Some of you are going to end up in statistics. In statistics, you probably won't use systems of equations that much. But if you're going, college algebra, pre-calc, trigonometry, if you're trying to go into any kind of STEM or anything even remotely scientific, you're going to be using systems of equations. Those of you who end up in business classes, if you go sort of the mathier side of business where, you're trying to get one of those sort of high-level analyst positions or something like that, systems of equations are going to come up as well. So they definitely come up, and they're very useful to understand how to solve systems of equations. One thing I didn't get to last time, which I think is just fair for you to know as students, because sometimes we teach you things and then sometimes it's almost like we're afraid to tell you how this stuff gets used in the real world because then it may demotivate you or something. But it is very useful to know how these systems of equations work. In reality, systems of equations that get used these days are very, very large. So what you're probably going to end up doing a lot of times is having a computer calculate the systems of equations, solve the systems of equations for you. That's what you're going to do most of the time. So then the very reasonable question is, well, then why do I need to learn how to solve systems of equations algebraically if I'm probably going to have a computer do it for me? And the answer is, anytime you do any type of problem, you should understand how to do the basics of that problem by hand, because if you can't do it by hand, that means you don't really understand what you're doing, and using mathematics that you don't understand leads to a lot of problems, right? It probably means you're going to make mistakes. So we make you learn how to do basic systems of equations so that you understand how to use systems of equations, right? And then sure, then it's fine. Put them in a computer, not in this class, but like later down the road, if you're at a job and you have to solve a systems of equations, sure, have a piece of software solve it for you. But you're not even going to be able to get to that point of having a computer solve it for you if you don't really understand how systems of equations work, how to construct the system of equations, how to enter it into the program, and how to do these different types of things. So for some of you, that will be, to varying degrees. Some of you who are going STEM routes, you end up taking linear algebra. You'll have an entire class that is all about matrices in order to solve systems of equations. So and some of you will go into statistics and you won't really use it at all. So it just kind of depends what you're doing with it. If you're solving the simple ones we're starting off with, which are 2 equations and 2 variables, you can probably solve it by hand as fast as a computer can solve it. So at that point, you're not really gaining anything by having the computer do it for you. If anything, you're sort of cheating yourself out of knowing how to do it. Once you get to 3 equations and 3 variables, it's probably a little faster to have a computer do it, right? But and I don't emphasize that because the 3 equations, I make you do a few, but I don't make you do that many because I don't see the point in having you do 100 of those problems, right? Other classes may do that. I don't see the point because in reality, a few years from now, if you need to solve 3 equations with 3 variables, you're in all likelihood you're going to put it into Wolfram Alpha, right? Wolfram Alpha is just a free calculating site. It'll solve systems of equations for you. But hopefully you understand the basics enough to make it work for you, right? It's like statistics. People think they know statistics when they haven't taken a statistics class, and then actually it's quite dangerous because you hear people in the news, politicians and news people and stuff quoting all these statistics, and if you know statistics, you go, oh, that person's like using that information completely wrong. But if you don't know statistics, you don't know that. Algebra is the same way, right? If you're going to use algebra, you kind of need to know how to use it properly. Otherwise, you're going to make bad business decisions. You're going to make bad research decisions, whatever it is that you're trying to do. So I just want to be honest with you. Especially the world we live in, the way data is collected, we have massive, massive data sets, which means the systems of equations that we try to solve are really big now. Like when I was doing my undergraduate work, my advisor, he was talking about how, when he was in grad school, and that was probably like the 80s, he had to solve 100 equations with 100 variables. He had to solve it by hand. It took him a whole semester because back then you just didn't have computers everywhere that could solve that kind of stuff. When I was in graduate school, I had systems of equations that were thousands of equations with thousands of variables that I was working on, but I was able to have a computer do most of the work for me. So, thousands of equations with thousands of variables, that would essentially be impossible to do in a lifetime. But I'm able to have a computer do it in, a few days. It could crunch all those numbers and sort of figure it out for me. So it is true that the computer will probably do a lot of the heavy lifting in the future for you if you have to solve systems of equations, but you should understand like what's going on when that happens. Okay. Also, if there's any kind of questions or anything, like I haven't been getting really too many emails from this course. So to me, I assume that means people are pretty good. I know some people have asked for homework extensions. Remember, if I have the homework set up correctly, unless I missed a setting somewhere, you should still be able to work on the homework after the due date. You just get partial credit for it. So I think that's reasonable. It's not like you get a 0. You can still keep working on it, and you still get some points. So remember, you can do that. Other than that, haven't really been hearing much from this class. So, I go by, when we're on this distance learning, the whole no news is good news. I assume that means students are doing well. 1 second. Okay. Thought I was going to sneeze. I assume that means students are doing well. So, so let me know if you have any questions and we'll go ahead. Otherwise, I'm going to move ahead with things. So quick review of our last discussion was about systems of equations. Where's my cursor here? There it is. Okay, so we talked about systems of equations graphically, and we talked about how you could have a system of equations. It just means you have more than one line, right? Oops. Oh, great. Now I got the hiccups. Let me grab a water. I got the hiccups here. Okay, sorry about that. Rough morning. This illness is rough. Okay, so let's see. Second equation. Let's make this a little different. Oh, what's the one I'm trying to do? There we go. This one works. And let me move it over so you can see it better. Okay, systems of equations. This is the picture you're gonna think of like 95% of the time. This is what's gonna happen. We have two equations. Notice that both equations have two variables. So the first equation is an x and y. Second equation is an x and y. And they intersect at exactly one point. This is kind of what you expect to happen. This is like the normal thing. We can get a couple different types of answers, solutions to these problems. But there's kind of the weird cases. This is what you usually expect is going to happen. So that is, we have two lines. They intersect at exactly one point. Remember, the points on a line are solutions to that equation. So if we want solutions to the system, that means we want solutions to all the equations. So it looks like this point 2, 3, this intersection point, that's a point on both lines, meaning it's a solution to both equations. So if I take x equals 2 and y equals 3 and plug it into both of these, it should work, right? So let's try it. If I plug that in, 2, 3, I'd get 4 minus 1 equals 3. Yeah, that's right. So that's how you check it. Now, technically, you have to check both equations in order to verify that your point is correct. And I know as students, I think sometimes play kind of like they think about it from a probability standpoint, and they're like, well, if it works for one, isn't it pretty highly likely that I got it right? And the answer is actually surprisingly not necessarily. So it depends on where you make your mistake in the problem. If your mistake was made at the very end when you were solving for the second variable, you will end up with a point that's on one of the lines, but not the other one. Okay, so you might think, oh, I tried it and it worked in one of the equations, so aren't I good to go? No, you got to check it in both. If you want to get the problem right, you really should check it into both equations. Otherwise, it happens way more than you would think that the solution you came up with is a point for one of the equations and not the other. So if it's something where you're risking points, just check it, right? It's way faster to check it than get it wrong and either miss something on the test or have to do a whole new problem on Delta Math or something like that. Okay, so that's what you expect. We ran into problems, we said, which is what's going to lead into what we're talking about today, which is something like this. Notice our intersection point is in the middle. That's really hard to tell what that exact answer is. And I know a lot of times people are like, why do we have to be so exact? Why can't we just kind of know? Well, if you're running a company, you don't want to know kind of how to maximize profit. You want to know exactly how to maximize profit. And if you're doing some kind of high-end engineering, you don't want to know like, well, what's some parts for our new telephone we're designing that kind of work? You want to know ones that like exactly work, right? So you want to make sure we want to find exact answers. The algebraic methods that we use are going to help us do that. These algebraic methods we're looking at as well are helpful here when we're solving systems of equations, but they actually come up in other areas of mathematics as well. So this will help you out if you understand the substitution method and you understand the elimination method. Both of those carry over into other ideas that later on you're going to be learning in college algebra or whatever, and you're going to go, oh, this is like substitution. Okay, I get it. Or this is like elimination. Okay, it's kind of similar. And you're like, you already know half of what you're supposed to do. So it's lots of useful information that I know sometimes students think this is kind of a waste of a chapter. It's actually way more helpful than you probably think. Okay. Okay, so that's what we expect. Excuse me. Okay, then we have the other two situations where we have, say, the following: y equals 2x minus 4, where we have parallel lines. Parallel lines have no point of intersection, which means there is no point that lies on both lines. Therefore, there is no solution. So this is the image you want to have in your head for no solution. It's harder, like it's a lot easier to see these solutions graphically when you're looking at the graph. But when we're doing everything algebraically, it's really easy to get separated from those types of solutions. And a very common mistake I see is students will mix up the two weird solutions. So the one that has an infinite number of solutions and the one that's no solution, students will mix them up. But you want to be able to sort of have this picture in your head and say, oh, this is like two parallel lines. They never meet, so the answer must be no solution, right? You don't want to do that whole problem and then give the wrong conclusion and still end up missing most of the points. That's kind of a bummer. Okay, and then there's the last scenario where we have something like the following. Like this, where two lines may look different at first, but they actually are just a different form of the same line, meaning they're right on top of each other. This is what we call a dependent solution. This has an infinite number of solutions. And so then that's the one where we have that kind of weird way of writing it, where we write it in that set builder notation with the curly brackets and the line and stuff, where we go through and do that. Okay, so that's our quick review of what we talked about last time. Hopefully that's all familiar to you and you're comfortable with that, because now we're going to do it from an algebraic perspective, and you're not going to have like the nice pictures to look at. I mean, I'll probably throw one on here, but you're going to be looking at the algebra, which makes it a little bit harder to kind of follow what's going on. So there's two methods of solving systems of equations algebraically. There is substitution and there is elimination. They both will work all the time. So any system of equations that I give you, you can choose to solve it using substitution. Any systems of equations that I give you, you can solve using elimination. So a reasonable question is, why do I need to learn two ways? If I can just get really good at one way and use that way 100% of the time, then why can't I just do that? And technically you could. The problem with doing it that way is that there are some problems that are going to be way easier to use one of these methods than the other. So there are some problems where if you solve it using substitution, you'll be done in like a few lines. But if you try to use elimination, it's going to go on and on and on. And same the other way around, where the substitution method may get very messy with fractions and stuff like that. Whereas elimination ends up being pretty quick. So as we do these problems, I'll go ahead and I'll point out when is a good idea to use one versus the other. I'll be honest, I don't really care. In this class, I need to know that you can solve systems of equations. I'm not going to get too hung up on, do it this way or do it this way. That's part of, I think, the learning process is you as a student deciding, oh, I think I want to do this problem as a substitution. Oh, this one I think I should use elimination, and going that way with it. So, use whichever way you can. But when you leave this class, one of the skills that you need to be leaving it with is the ability to solve a systems of equations one way or another. Okay. Right. So let's do an example here. So let's, what would this look like? This will look like solve. So let's say solve or solve the systems of equations or something, and then we'll have our system of equations. Okay. And I'm going to make sure I wrote this down correctly. This is one of those sections where, like, you know, when the problem appears up on Delta Math and then you write it down on your piece of paper, just take an extra second to double check that you wrote it down correctly. Because I see this happen a lot in this chapter where a student will call me over and say, you know, I've done this problem like 3 times and I swear I'm doing it right, but it doesn't match the actual answer. And then we look and the person wrote the problem down incorrectly, right? It's easy to do where instead of making this a -17, you make it a -16 or something like that. So yeah, you did the problem 3 times, you did the mathematics correct, you just did it for the wrong problem. So I see students lose a lot of time on that, so it's worth a second or two to just double check. Did I do this right? Looks like I did, so we can move forward. Okay, so step 1, right, we're only learning, we're going to learn substitution, then we're going to learn elimination. We'll see if we get through elimination today or not. We may or may not have time to finish that one, but we'll definitely get through substitution here. The first thing I need to do when handed a system of equations that I'm told to solve, and I think I'm going to have to solve it algebraically, which is going to be most of the time, I have to decide which of the methods I want to use. The way that sort of the key that you should be looking for if you're going to use substitution is that the problem is probably going to be easier using substitution if one of the coefficients in your equations is a 1 or a -1. So that is, you have like, and we don't usually write it 1y, right? We write it y. So see how we have a plus y there? That's kind of a hint to me. That's calling out to me, I probably want to use substitution for this problem. It's probably going to be easier that way. If we had a -y, we could do the same thing, because if we have a -y in there, we can still solve that for y. And then it makes the substitution pretty clean in general. Okay, so here's what we're going to do. So I'm deciding, okay, I'm going to use substitution here. So here's your step 1. Solve for one variable. So what you're going to do is you're going to solve one equation for one variable. And your best choice is going to be to solve for that variable that has the coefficient of 1 or -1 on it. That's the whole reason that this method is easier that way. So see how I have a coefficient of 4 here on this 4x, 1 on this 1y, -2x here, and a 3 on the 3y. Now, let's try to understand why substitution is easier if I have a coefficient of 1 or -1. Well, let's consider this 3y over here. What if I decided that's the variable I'm going to solve for, is this y right here? Well, at some point in doing that, I'm going to have to divide by 3, right? Because I have to get y all by itself, so I'll have to divide this 3 out. But what happens to the rest of the equation when I do that? Well, this over here would become a fraction, and this over here would become a fraction, right? This would be -2/3. This would be -17/3 when I divide by 3. And mathematically, it would work, right? But why do we want to create a ton of steps that have fractions in them if we think we can do the steps without introducing fractions, right? It just makes more sense. If you do things the more complicated way, not only is it going to be a lot more work, you're more likely to make a mistake. So I'm choosing to solve for the way that's going to make it easier. I'm going to solve for this y right here. So how would I solve for that? I'm going to subtract 4x from both sides. So doing that gives me y equals -4x plus 13. Okay, y equals -4x plus 13. So I've solved one equation for one variable, right? That's what you want to get. It doesn't matter if you choose x or y. Choose whatever you think is going to be simpler. I mean, even if you make the worst choices, that's going to be the most amount of work, you'll still get to the right answer. It's just that you're going to do, you know, if you make poor choices, you might do 10 times as much work on the problem than the person next to you makes the really good choices. They'll just finish earlier. But even if you make a bad choice, you're not going to get the problem wrong. It's just going to be harder to do. Okay, so this is the easiest way. I'm going to solve for that variable that occurs in the first equation. It's a clue that has a coefficient of 1, so I'm going to solve for that. Now what you do is you use this substitution to substitute into the other equation. So what is this equation really telling me? It's telling me that y is the same as negative 4x plus 13. In other words, wherever I have a y, I could just replace that with negative 4x plus 13 because they're equal to each other, right? That's exactly what we're going to do. This is our guide for our substitution. So now step 2 is use the substitution. I get that? Nope, didn't get it. Substitution. I think that's right. Use the substitution from step 1. That might be off the screen. I can move this over a bit. Now you're going to use that substitution from step 1. Okay? I'm going to have to scroll up a bit here. So what I'm going to do now, and you have to use the other equation. You can't go back and use the same equation that you just solved for. You have to use both equations in your system. Otherwise, you're not going to be using all the information available. Each of these equations has information encoded inside of it, and you have to access all of that to get your answer. So whichever equation you use in step 1, you substitute into the other equation in step 2. So let's write what that looks like. So I'm going to take negative 2x plus 3y equals negative 17. That's my second equation. And see where this y is? I'm going to replace it with what y is equal to, which is negative 4x plus 13. Okay, so let's do that. And usually it's better, wherever the variable goes, throw some parentheses there, and you want to leave a little bit of space so that you can write in it where it's doing it on the screen here. It's not going to put any space. But generally, you want to put your substitutions inside of a parentheses because, like as you'll see here, we're going to end up having to do a distributive property. When people don't write those parentheses, they forget to do the distributive property, and then your whole problem is going to be wrong, and you're going to have to start over again, right? This problem's not too bad, but especially when you do like a 3 variable systems of equations, which could take, those can take like 10 minutes to do. It's frustrating to spend 10 minutes on it and then go back and realize you made a silly mistake at the beginning and have to start all over, right? That's sort of demoralizing. So I'm putting some parentheses here, and then I'm going to put my substitution in there. Instead of y, we're going to put negative 4x plus 13. Okay, so do you see that? It looks way more complicated, and, maybe it is. We could argue that it is. But all I really did was I took this original equation that we had, and instead of writing y, I wrote what we said y is equal to, which is negative 4x plus 13. And you might look at that and say, well, yeah, it seems like you just made it worse. But there's something to notice here. This equation is now in one variable. See how we just were able to transition from equations that had 2 variables to an equation with 1 variable? Well, the good news is you know how to solve equations in 1 variable, right? That's much easier than solving a systems of equations. So that's what you fall back on now, is like your beginning algebra work to solve this equation right here. Right, so that's going to become what? We're going to have negative 2x minus 12x plus 39. If you see me make a mistake, go ahead and call it out. We'll save some time that way, because sometimes I do make a mistake here and there when I'm trying to keep track of too many things while I'm teaching. So negative 2x minus 12x plus 39 equals negative 17. So all I did there was my distributive property. Okay, I just distributed that 3 in. And remember, since I have my parentheses here, I remembered to distribute properly. Okay. Okay, so now when we start combining like terms, negative 2x minus 12x is going to be negative 14x plus 39 equals negative 17. Okay. Now, see how it's getting easier? Now we can solve this. So by subtracting 39, hopefully this is coming out right, negative 14x. So if I subtract, it's going to be what? Negative 46? No. Yeah. 56? Double check here. $56, yeah. And then divide by 4 should be what? 4? Yeah, 4. Okay, so when we divide, we get x equals 4. Oops, I'm off the screen here. And I will be right back. All right, sorry about that. I had to get a tissue. Okay, so we got x equals 4, right? If there's any questions, speak up and let me know, because I can repeat what we just did. But notice we haven't solved the system of equations. What is a solution to a system of equations? Well, remember, it's two values. In this case, we have x's and y's, so we need an x value and a y value. Some of the mistake that people make when they do their very first systems of equations is they think they're done. They get to x equals 4 and go, oh, great, we solved for x, we're done, right? No, a solution to a system of equations has two parts. In this case, an x value and a y value. You got to get both of those. But the good news is we've done the hard work, or the harder work. Going back and solving for the other variable isn't bad, because take either of these first two equations, just pick, it doesn't even matter at this point, pick whichever one looks easier. By step 2, you have to make sure that you've used both equations, but by step 3, it doesn't matter which one you choose. So step 3, solve for other variable. You solve for the other variable, in this case the y variable that we haven't solved for yet. So pick whichever one looks easier. I'm going to take this first one, 4x plus y equals 13. I'm going to take that, and I'm going to solve for that. So I go back, I take my original equation, but we know that x is equal to 4, right? So I don't have to write 4x plus 13 anymore. We know x is 4, so I can write this as 4 times 4 plus y equals 13. Yeah, good. Looks like looks like I didn't make any mistakes. This is gonna come out right. So this is gonna be 16 plus y equals 13, or y equals -3. Now we've solved it. See how fast it was to get that second variable? Almost like what, 80% of our work was to get that first variable. Once we got the first variable, it took us what, like 30 seconds and 4 lines in order to get the other variable. It's not bad at all, right? So just make sure you get them both. So the solution here, I think if I remember right, many of the Delta math problems, they want you to give it as a coordinate, so like a point. So they're kind of doing the point interpretation, whereas you know, sometimes programs will also have you say x equals blank and they leave it blank for you to fill in, and y equals blank. So either of those answers are fine. Like when I'm giving written tests, if students give me the solution in the form of a point, I take the answer, get full credit. If students give it to me as x equals 4, y equals -3, I give full credit, because either way is a legitimate interpretation of that solution. But for the Delta math, just pay attention to how they want the solution. I know sometimes they want it as a point. I forget about every single problem that you run across, but usually they want it, or sometimes they want it as a point. So that, in other words, there's 2 ways that are really considered acceptable to give this solution. One way would be to write it as the point, 4 comma -3, right? That's sort of our, that's thinking of it in terms of a graph. We've given an x value, we've given a y value. That's a totally legitimate way of giving that solution. The other way that students sometimes like to do it, which is totally legitimate, is just to say x equals 4 and y equals -3. So both of those ways, if you think about it, give the same information, right? As a point, this says x is 4, y is -3, or you've written it out explicitly. Either way, you have figured out the solution to the system of equations, right? Now, you know, people kind of forget this, I think. They think, you know, they get so used to some textbooks you've had, you can look in the back of the book to see if it's right. When you put an answer into Delta math, it's going to tell you if you're right. In real life, no one ever tells you if your math is right, right? It's just that your business will fail, or your research will go badly, or whatever, because you have mistakes in it, right? So it's always worth checking. And like I've mentioned, with systems of equations, super easy to check. It took some work to find, right? That was not insignificant. I wouldn't say it's super hard, especially when you get the hang of it. But there's some work here that you had to work through. But checking it, very easy. So let's just take it one at a time. Let's take our equations. So I'll take this one. And we're going to go put it here. So I'm going to take my first equation, which is 4x plus y equals 13. And I'm just going to plug in the values that we found. So 4 times 4 plus -3. And so I just want to ask myself, so I've plugged in my 4 for x and my -3 for y. And I just ask myself, does this make sense? Let's see. 16 minus 3 equals 13. Yeah, that's true. That's true. Okay. Okay, good. Now we check the other one. So now I take the other equation. Let's see, where is it? Way up here. And I grab that. And let's put it down here. So I take the second equation, and I'm just going to do the same thing. I'm going to plug in our values. So that's going to be x is 4. And y is -3, and then just ask ourselves, as soon as it recompiles here, does this work? So this would be what? -8 minus 9 is -17. Does that work? Yep. We know 100% we have this problem right. Well, how do we know that? Because we just verified it in both of the equations. And we know that a solution to a system of equations is a solution to both. We just confirmed that 4 comma -3 is a solution to both of those equations. So we totally know that we got that systems of equations correct. Okay, so that's how they'll work. Like I say, pretty much everywhere you look, this is exactly how it's taught. There's not like a bunch of different ways to teach this. So wherever you want to look at this, whether it's the videos I posted, you want to look at other videos, anywhere you look, you're probably going to basically find the same basic method for going through and solving your systems of equations, right? So that is the substitution method. Let's see. 9 minutes. Definitely don't have time to start with elimination and addition. So I have time to show you a couple other things. So one thing I want to say about the other method that we'll talk about next time, it is sometimes called the addition method and it is sometimes called the elimination method. They are the exact same thing. Okay, so if you used a book in high school that called it the addition method, and now we're teaching you the elimination method, it's the same exact thing. There's no difference. So it just doesn't really matter what the name of it is. What matters is, do you know how to use that? And we don't have time to get into it. I will show you next time how to do it, and we'll go through and we'll work through that. But first, I think I have enough time. I can show you what happens when we get like one of those other types of problems, when we get like like I say, most of the time you're going to get this kind of situation. You have a system of equations, you solve for a solution and you get a solution and you go, great, I'm good. I got my solution. Everything's good. But what about those, remember the parallel lines, the no solution type thing? Well, we know how to recognize that on a graph. It's when you have parallel lines. But how am I necessarily going to recognize that when it's just a system of equations on the paper? Because a lot of times you're not going to recognize that those are parallel lines. Maybe if they're all in slope-intercept form, you'd recognize that, but that's not likely to happen with systems of equations. So let me find that problem. Here we go. Let's try this one. Okay, so solve. And I'll move a little quick because I have 7 minutes. I want to make sure I get through it. I think we will. I won't have to go super fast. Also, remember, if there's questions, feel free to ask. Y equals 2x plus 4. Okay, y equals 2x plus 4, 8x minus 4y equals 7. Okay, so here's the systems of equations. When I look at that, I don't think anything's weird at all. Right? When I look at this, I don't go, I bet those are parallel lines. And it's not a thing that jumps into your head, right? They just look like a system of equations with these different equations in it. So what do? Well, step 1, solve one equation for one variable. Awesome. That's already done, right? You could solve for one of the other variables if you want, but why would you? Step 1's already done for us. We have y solved for by itself already. Great. So we can jump straight to step 2, which is to substitute into the other equation. So when I do that, I'm going to get this equation again, except I'm going to substitute into it. So instead of writing y, we're going to write 2x plus 4 because that's what y is equal to. Right? That's what y is equal to according to this up here. So I changed my y into 2x plus 4. All right, so now let's progress through where we solve this system, or we solve this equation. So that's going to be 8x minus 8x. Oh, yeah, some of you might already see what's going to happen here, right? But if not, that's okay. All right, we'll continue. Minus 16 equals 7. So all I did was the distribution there. And now I simplify the left side and go, wait, what's happening here? This is weird. This is a strange outcome. My 8x's cancel, right? Because 8x minus 8x is no x's. So I end up with negative 16 equals 7. Now this is a little bit weird. We haven't run across this before. Here we have an equation with no variables in it, and it's false. So remember, the variables, we can choose different values and plug them in and see if they work. But it actually doesn't matter in this case because your variables cancel out right away. Right? Now, all the variables have canceled out. There's nothing left down here. In other words, It doesn't matter what I choose for x or what I choose for y. Those variables cancel each other out. And what I'm left down here is a false statement. So this is the part, don't memorize this. I see students come to wrong conclusions because they've tried to memorize this. Just think about it for a minute. If we're ending up with an equation that is false, negative 16 does not equal 7. That's a false statement. Do we think that that should imply that there's an infinite number of solutions? Or is it more likely that this false statement implies that there is no solution, right? It makes sense that it would imply to us there is no solution. There's no values for x and y that's going to make negative 16 equal 7. That can't happen, right? Excuse me. So this is where we get the no solution type answer, right? No solution. And I forget off the top of my head the way that they want us to answer that in the Delta Math, but just pay attention to it. It'll be one of your options for those types of problems. So this is where you would get no solution. The other outcome is if you solve the equations and all your variables disappear and you're left with a true statement. That's the other case where the lines are right on top of each other. Okay, that's a dependent system. So then you would answer it that way. We looked at that last time with the set notation to describe that set. Okay, but when it's false like this, that's no solution. And that makes sense. Negative 16 can't ever equal 7. Those two things will never be equal to each other. So how could there be a solution, right? So that's how we take care of those types of problems. So you can definitely move ahead with the substitution. Those of you who want to move ahead with the other method, the elimination method, feel free. Just by watching videos, you can probably work through it. So you're welcome to move ahead and do that. I will talk about the elimination method next time when we meet. With that said, I'm going to shut down the YouTube stream. Anyone who wants to talk to me in Zoom is welcome to jump in there and ask me questions, anything about the class, how the class functions, have a homework question, any of that kind of stuff. Come in and talk to me about it. Otherwise, I will see you next week. Okay, thanks everybody.